Hello everyone. In this video I'm going to be doing a quantum mechanics question, one that's on simple harmonic motion. This was a question on an exam, and it should give you some insight into the kinds of things that you should know to do the problem quickly. This video is a remastered version of the one I did before. The volume has been turned up, the video resolution has been increased, as well as the lighting on my face. So if you want to be stronger than you were at the start of the video, pause at some point and try and make progress on your own. With that said, here we go. At t equals 0, the wave function for a one-dimensional simple harmonic oscillator of mass m and angular frequency omega is this, where a and b are complex numbers, and psi n is the nth eigenstate. What relation must a and b satisfy? Suggest you normalize the wave function. Okay, so the wave function, the reason we care about the wave function is because that if you take its magnitude and square it, it gives you a probability density for the particle's position, and the total area under the curve must be equal to 1. That's a basic fact from probability. So this is called a normalization when we say that 1 is equal to the integral over all values of x from minus infinity to positive infinity of the modulus of psi x0 squared dx. So the modulus squared of a complex number is psi star x0 times psi x0 dx. Now, when I say star here, I mean the complex conjugate. So I am going to, so the complex conjugate of the given function here is going to be a star psi 1 star plus b star psi 2 star. And for psi x0, we just have the function a psi 1 plus b psi 2 dx. Okay, and now I'm going to expand the integrand by using the FOIL method. So multiplying the first terms here, that's going to be a star a psi 1 star psi 1 plus, and now the outer terms, a star b psi 1 star psi 2 plus b star a psi 2 star psi 1 plus, and now the last term is b star b psi 2 star psi 2 dx. All right, so now I use the fact that the integral of a sum is the sum of the integrals. I'm going to split up this integral, and I will bring the constants out in front of each one. So for the first one here, we have a star a times the integral of psi 1 star psi 1 dx plus a star b integral psi 1 star psi 2 dx and plus b star a integral, that is psi 2 star psi 1 dx plus b star b integral psi 2 star psi 2 dx. Now, the eigenstates of the harmonic oscillator are very messy functions. Psi 1 is a constant times x times e to the negative x squared with a constant up there, And it's just a very time-consuming endeavor to evaluate these integrals by brute force directly. It's better to solve them. It's better to evaluate them indirectly by with the fact that all of the eigenstates are considered to be orthonormal. What that means is this integral here is going to be 1 because this is psi 1 and this is psi 1. The first and second eigenstates are orthogonal, so this integral here is going to be 0. The same with this integral here. This one here is equal to 0. This one here, because this is psi 2 and psi 2, they're the same, so this is equal to 1. So again, I'm using the property that the eigenstates are all orthonormal to evaluate these integrals quickly. So what we're left with then is a star a plus b star b. And from using this can be simplified using the modulus squared. And if you remember, this is equal to 1. So this is our relation involving A and B. All right, let's see what is next here. What is the time-dependent state psi xt? Okay, so this one here isn't... So the problem gives us the wave function at t equals 0, and the question is asking for the wave function at a later time, t. So a psi 1x plus b psi 2x. So we get psi xt very simply by multiplying each term by the respective wiggle factor. So for the first term here, it's going to be a psi 1x times e to the minus minus I e1 t over h bar. And I use e1 here because this is psi 1. This is the for the first eigenstate, and plus. And now the second term, b psi 2x. I multiply this by the appropriate wiggle factor. So because this is a 2, I'm going to use e to the minus I e2 t over h bar. So this is 2 because this is 2. Now, for a harmonic oscillator, the energy of the nth eigenstate, En, is n plus 1/2 times h bar omega. Now, E1, if I plug in n equals 1, that gives me 3/2 h bar omega. And if I plug in n equals 2, I get E2, which is 5/2 h bar omega. Now, these energies both have h bar, so you see that we divide, the h bars will cancel out. So what we're left with then is psi xt equals a psi 1x e to the minus 3I omega t over 2 plus b psi 2x e to the minus 5I omega t over 2. And this is our final answer for the wave function at any future time t. Now, in order to simplify the forthcoming calculations for the next part, where we calculate the expectation value of the position and momentum operators, it's very helpful to use what's called bra-ket notation. If we look back here at our previous work, each of these integrals here can be interpreted as an inner product of two complex functions. So for this first integral here, I can write it very compactly as psi 1 comma psi 1 within within angled brackets here. This is a very convenient way to write the integral dx of psi 1, what we have here. This integral here would be psi 1 comma psi 2. You'll notice that this first function here is the one that's complex conjugated, and the second function here is the one that's not. Every inner product here can be thought of as the product of a bra and a ket. This here is what's called a ket. That's spelled K-E-T. And this here is the bra, B-R-A. And it, so rather than writing out each of these integrals here, it's very helpful to just write it as these two. It will be, so if we were to write the ket and bra of this boxed formula for psi xt, let's start with the ket. So psi xt. Now, these integrals here are in dx. So a and any function of time is considered to be a constant. So this would be a e minus 3I omega t over 2 times the ket psi 1, and similarly plus b e to the minus 5I omega t over 2 ket psi 2. And if I, and now I'll do the same for the bra. So bra psi xt. I have to, remember I have to take the complex conjugate of the, to get the bra. So this will be a star times e to the 3I omega t over 2. And this will be bra psi 1 plus b star e to the positive 5I t, 5I omega t over 2, bra psi 2. So why are we doing this? That's because when we go to calculate the expectation value of the position operator at time t, so this is important. This is going to be this is how we evaluate the expectation value. We take the inner product with the operator in between using psi xt. It's important that you don't put psi x0 in place of these here. If you did, that would be the expectation of the position operator at time t equals 0. But the question here is asking for the expectation value at time t. So that's very important that we use psi xt here rather than psi x0. Now, we could just replace x hat with x and evaluate the integral, but again, that would be very time consuming because psi xt is in terms of psi 1 and psi 2, and the integration would be a mess. So it's best to evaluate this indirectly using the using bra-ket notation, and the fact that the position operator can be expressed very conveniently in terms of ladder operators. So this is equal to psi xt, and now h bar over 2m omega a plus hat plus a minus hat. Now, the reason these ladder operators, so the way these ladder operators work is that if they are applied to some a ket, so a plus hat acting on the nth eigenstate will give you square root n plus 1 and give you the next highest eigenstate. Whereas if we apply the lowering operator to the nth eigenstate, that gives us square root n times the next lowest eigenstate. So because we wrote ket psi xt and bra psi xt in terms of psi 1 and psi 2, these operations here will be very simple compared to just integrating it by brute force. So again, this expectation or this inner product here represents an integral. So I'm going to bring this constant out in front. So this is square root h bar over 2m omega times inner product psi xt, and I have my operators a plus hat plus a minus hat psi xt. This inner product represents an integral, so I'm going to split it up. H bar over 2m omega, and now I'm going to use two colors here. This is going to be, for the first term, I'll have psi xt, a plus, and the second term here, which is, so because I have a plus here, that's going to, this plus sign here is this plus sign here. And now the second term, psi xt, a minus psi xt, and close bracket. So now I'm going to plug in the formula. I'm going to write down the formulas for the bra and the ket for each of these inner products. So in yellow here, the bra psi xt, that is this one here, a star e, okay. So this is a star e to the 3I omega t over 2, bra psi 1 plus b star e to the 5I omega t over 2, bra psi 2, and yes, I did that correctly. Okay, and now I have my operator here, a plus, and now I put the formula for the ket. So that's going to be this one right here. So a e to the minus 3I plus b. Okay. So I have a e to the minus 3I omega t over 2 ket psi 1 plus b e to the minus 5I omega t over 2 ket psi 2. And this is this inner product expanded, the one in yellow. So now I'm going to write down the same thing for the orange term, but have an a minus here instead. So just give me 1 second to write that out. A star e to the 3I omega t over 2 bra psi 1 plus b star e to the 5 I omega t over 2 bra psi 2 a minus, and now e to the minus 3I omega t over 2 ket psi 1 plus b e to the minus 5I omega t over 2 ket psi 2. And I can't forget to close the square bracket here. Okay, so now each of these operators will act on the terms in front of them. So a plus will operate on this term as well as this term. Now it's important to note that operators act on kets. So this a e to the times the function of t will be treated as a constant and pulled in front. So a plus will act specifically on ket psi 1, and for the second term it'll act on ket psi 2. A minus here similarly will act on ket psi 1 and ket psi 2. So if we and in doing so we will use these rules here. A plus will result in square root n plus 1 times the next highest eigenstate, and a minus acting on a ket will result in square root n times the next lowest eigenstate. So this is equal to square root h bar over 2m omega. And now I'm just going to copy this to save time. And whoops. I will have a e to the minus 3I omega t over 2, and now a plus acting on ket psi 1, that's going to be square root 2 times the next highest eigenstate, ket psi 2, plus b e to the minus 5 I omega t over 2, and now a plus acting on ket psi 2, that's going to give me square root 3 times ket psi 3. Now we move on to the orange terms. So plus, I'm going to copy and paste this to save time. All right, and now a minus, so this, the second term here will become a e to the minus 3I omega t. So this will be, this will result in square root 1, which is just 1, and then times the next lowest eigenstate, which is ket psi 0. This is the ground state of the harmonic oscillator. And now plus b e to the minus 5 I omega t over 2. A minus applied to ket psi 2, that will give me square root 2. times the next lowest eigenstate, which is ket psi 1. And close square bracket. All right, so now we have to multiply this all out using the FOIL method. So if we multiply these first terms here, the bra psi 1 and the ket psi 2 will combine to form an inner product psi 1 comma psi 2. That will be 0 because the first and second eigenstates are orthogonal. So these first terms, multiplying these first terms, will yield a 0. If we multiply the outer terms, the bra psi 1 will combine with the ket psi 3 to result in an inner product of psi 1 comma psi 3. That again will be 0 because the first and third eigenstates are orthogonal. Multiplying the inner terms, we have bra psi 2 and we have ket psi 2. The product of those will give us an inner product that is 1. So multiplying the inner terms will yield a non-zero result. And multiplying the last terms, bra psi 2, with multiplying that with ket psi 3, that'll give an inner product that gives 0. So there's only one term that survives from the yellow expression. So let me go ahead and write that before we talk about the orange expression. So this is square root h bar over 2 m omega. So the term that survives is going to be b star a. And if I multiply the exponential functions, 5 halves minus 3 halves, that just gives me 1. So this is times e to the I omega t times square root 2, this one right here. And I believe, yes, that's it. So now from the expression in orange, if we multiply the first terms, bra psi 1 will combine with ket psi 0 to give us an inner product that's 0. So this term does not contribute anything. Multiplying the outer terms, bra psi 1 will combine with ket psi 1 to give us a non-zero number. So let's go ahead and write that in. So plus a star times b, and now e to the, if I combine the exponential function, that's going to be times e to the minus I omega t, and I have a square root 2. And again, this inner product here, psi 1 comma psi 1 is 1. Let's see, I'll just go through to check that we have no other non-zero terms. So multiplying the inner terms, bra psi 2 with ket psi 0, that inner product is 0 because the second and ground states are, the second eigenstate and the ground state are orthogonal. Multiplying the last terms, bra psi 2 with ket psi 1, that inner product is 0. So this is our formula for the expectation value of the position at time t. Now I'm going to factor out the square root 2 so that it gives me square root h bar over m omega, b star a e to the I omega t plus a star b times e to the minus I omega t. Now this formula here can be simplified by using the fact that a and b are complex numbers. So in general, a complex number z can be written in rectangular form as a plus ib, where a and b are real numbers. It can also be expressed in polar form, which is the magnitude times e to the I phi, where phi is the counterclockwise angle from the positive real axis. So I'm going to say that A is the magnitude times e to the I phi A, where phi A is some phase phase factor. And similarly for B, I can write down magnitude of B e to the I phi B. The point of doing this is to simplify this formula here. So using this, it becomes square root h bar over m omega b star. That's just going to be, so the magnitude of a and b are real numbers, so these don't change. So b star, that's going to be e to the minus I phi b, and then e to the I phi a, and then e to the I omega t, plus a star, that's going to be a star b, that's going to be magnitude a, magnitude b, e to the minus I phi a, e to the I phi b, times e to the minus I omega t. So I can factor out AB, or magnitude A, magnitude B. And if I combine the exponential functions, I'm going to factor out the I, so I will get omega t plus phi A minus phi B. That's for the first term, and now for the second term, I get plus e to the I. I'm sorry, this is minus I, and it will be the same thing. Plus phi A minus phi B. And if you remember, cosine, the cosine can be defined in terms of exponential functions as e to the ix plus e to the minus ix over 2. What we have here is what's in the numerator, so I'm going to multiply both sides by that. So this is 2 times the cosine of omega t plus the phase difference. This is square root h bar over m omega, magnitude A, magnitude B, and times 2 times the cosine of omega t plus phi. Now I'm using phi here to represent the difference in phases. This is an arbitrary constant, so it can be anything and the final answer will be correct. So this here is our final expression for the expectation value of the position operator at time t. Notice that it is a function of time. So the way we calculate the expectation value of momentum quickly is by recognizing that this is the mass times the expectation value of velocity. And the expectation value of velocity is the time derivative of the expectation value of position, which is what we just calculated. Now this is m times, so if I take the derivative of this, that's going to be square root h bar over m omega. So I'm going to have sine with a minus sign. And using the chain rule, I have to multiply by the derivative of what's inside with respect to t. That gives me an extra omega on the outside. So therefore, the expectation value of momentum is minus 2 square root h bar m omega, magnitude A, magnitude B, sine omega t plus phi. And this is the final answer. All right, everyone, thank you for watching. If you made it this far, congratulations.